some kind of a sum formula where we're adding formulas together. And I have to go to another document for that. I believe it's right here. Yeah. All right, so first thing we're going to do here is we're going to try to develop a formula. And they give it to you here, but they kind of have us try to figure it out. So I'm actually going to add a page here because I'm going to need a little bit more space, I think. So what they're asking us to do here in this investigation, they just give us the first 5 terms in sigma notation, right? So they tell us from I equals 1 to 5. So this is U1, U2, U3, U4, and U5. And they tell us it's geometric. So they're using the formula, right? The first term is just U1. The second term is U1 multiplied by R a single time, then U1R squared, U1R cubed, U1R the fourth. This is just using the U1 times R to the n minus 1 formula to generate those first 5 terms. So what we have here, I'm going to write this down, so S5. And remember, S is just a formula for the sum. One thing to remember is S1 is always just equal to U1. So S2 is U1 plus U2. S3 is U1 plus U2. Whoops. U2 plus U3. And et cetera, et cetera. And S5 is what we're dealing with here, which is U1 plus U2 plus U3 plus U4 plus U5. And this is a little formula you can actually do for any like nth term of the sum, but they want us to do it with 5 just to start off, and then I'll develop it for n in general as well. So for now they want us to write down an expression for RS5. So RS5 would be U1R plus sorry. They have it written out in like the R term. I'm actually going to do that first. Let's get rid of that. Oops. All right. So the way that they wrote it is U1 plus U1R plus U1R squared plus U1R cubed plus U1R to the fourth. So right underneath it, I'm going to write RS5. And I'm going to write it in a special way. I'm going to line up the terms that are the same. So if you multiply each one of these terms by R, the power is just going to increase for each one, right? So we're going to have U1R. I'm going to write that underneath the one above it. And then we're going to have U1R squared. And we're going to have U1R cubed. Basically, this one multiplied by R to get there. This one multiplied by R to get there. This one to get here. And then we'll have plus U1R to the fourth. And then we'll now have a U1R to the fifth. Sorry, I was getting to the edge there. Okay. So now they're going to have us subtract. So we're going to subtract the RS5 minus S5. So we're going to subtract this one from the one below it. So RS5 minus S5. A lot of these cancel. This cancels. This cancels. This cancels. This cancels. What we're left with, this one is positive. And this one, because we're subtracting it, will be negative. So it's equal to U1R to the fifth minus U1. So we can do a little factoring then. So if I pull the S5 out of the left side, I have S5 times R minus 1 is equal to U1 times R to the fifth minus 1. And now if we divide, we get S5 is equal to U1 times R to the fifth minus 1 divided by R minus 1. So this is a formula for the fifth sum of any geometric series, right? Series is when we're adding a bunch of terms together. And the form might seem kind of weird. You might want to go back and watch that proof again. But I'm going to do it in general now as well. So Sn is going to be U1 plus U1R plus U1R squared plus all the way to the end, we're going to have a U1R to the power n minus 1, right? That's just the formula for the nth term. So if I'm adding n terms together, I have the first term, the second term, the third term, all the way up to the nth term, which this is just the formula that we just derived for geometric sequence. So then if I multiply all those terms by R, so RSn is going to be U1R, right? Because we multiply this guy by R. Then it's going to be U1R squared all the way to the end. Eventually, we're going to get to U1R to the n minus 1. Technically, that comes from a term somewhere in the middle here, but we know it's going to be there eventually. And then the last one is going to be U1R to the n. Then if we subtract the top one from the bottom one, we'll have RSn minus Sn is equal to all these cancel. Everything cancels except for the first and last terms from the two series. So we're going to have u1 r to the n minus u1. And so if we do some factoring now, Sn times r minus 1 is equal to u1 times r to the n minus 1. So Sn is equal to u1 times r to the n minus 1 divided by r minus 1. And this is the formula in your formula booklet for the sum of the first n terms of a geometric series. So what do you need to know? You need to know u1, and you need to know r, and you need to know n. Those are the things you need to know to be able to use this formula. What's the first term of the geometric series? What is the common ratio? And how many terms are you adding together? So let's see here. Yeah. Part 3 of the investigation, I think we might come back to later. Let's do number 1 first, and then we'll come back up and we'll do the chessboard problem. So in a geometric series, the first sum is 3. That also means u1 is 3, right? S1 and u1 are always the same. Common ratio is equal to 2, so r is 2. Find the sum of the first 10 terms of the sequence. So n is 10. And hey, that's the 3 things we need. We don't even need to know what the last term is. So I'm just going to use the formula. So S10 is equal to our first term, 3, times r to the n. That's 2 to the 10th minus 1, divided by r minus 1, which is 10 minus 1. Head to the calculator for that one. Let's see. 2 to the 10th minus 1, and multiply by 3, and then divide by 9. I get 341. And sometimes it's nice to kind of think of this as in the right ballpark, right? The 10th term of the sequence, so u10, we don't need to know this, but u10 would be 3 times 2 to the 9th, right? Because it's always n minus 1. So 2 to the 9th times 3. Uh-oh. I'm not so confident in my answer now. Let's see if something weird happened. Oh, r minus 1. I'm so sorry, not n minus 1. Come on, Fransky. This should be 2 minus 1, which is definitely not going to be this answer. The reason I know it's wrong, and I'm glad I checked, is because the 10th term, the 10th term is 1,536. So what we're really trying to do here, we're trying to add 3 plus 6 plus 12, right? Because we're multiplying by 2 every time. And our last term is 1,536. Right? So it should be bigger. So 2 minus 1 is just 1. So it's just 3 times 2 to the 10th minus 1, which is 3 times, parentheses, 2 to the 10th minus 1, close parentheses. 3,069. That sounds better. There we go. Now they want the next 10 terms of the sequence. So a couple ways you can do this. One way is I could find S20 and subtract S10. Does that make sense? Because if you find the sum of the first 20 terms and then you take away the first 10, you'll end up with terms 11 through 20, right? So let's do it that way. We'll do it both ways that I'm thinking of here. So S20 is going to be 3 times 2 to the 20 minus 1 divided by 2 minus 1, which is 2 to the 20 is a big number, times 3. 3145728. 3145728, and I'm going to take away 3,069. And that gives us, here we go, 3142659. The other way you could do it is you could say, well, 1536 is term 10. So what's U11? U11 would be 1536 times 2. So that's 3,072. So let's pretend that's U1. Let's use a different letter. Let's call that V1. So V1, let's say, is 3,072. And we want the next 10 terms. So we could say we want n equals 10. And r is still going to be 2 because we're doubling every time. So you could use these 3 and use the same formula, right? We're saying basically we're creating a new sequence that starts at the 11th term. And we're going to multiply, and we're going to add all the next 10 terms together. So let's see if the same thing works out. So it should be then 3,072. I'm going to get a little sloppy with my notation here. times 2 to the 10 minus 1 over 2 minus 1. Let's see what we get. Brackets around that bottom. So 2 to the 10 minus 1 multiplied by 3072 does indeed give me 3142656. Oh, that's so close. Why are they off? 314, let's see. 3072. I get 3142656. Why are they different? Well, that's a conundrum. Let me just double check my math here. It should be the 6. Let's see. 3069. Oh, I wrote this down wrong. I'm sorry. This number is a 5. This guy. Sorry. This is a 5, which makes this a 6. I'm sorry. There we go. Okay, so both ways work the same way. This is why it's good to check your work 2 different ways, because twice I've messed up today already. Sorry about that. All right, so I'm going to go back to the chessboard question now, and then we'll do these last problems at the bottom here, and we'll be done for the day. So, first of all, let's do number 3 here. So this formula and this formula do the same thing, and they're both in your formula booklet. And the question is why this formula might sometimes be easier to use if r is less than 1. Well, if r is less than 1, that's like r is like 0.9. Then 0.9 raised to a big power is going to be small, right? It's going to get even smaller, like it could be like 0.1 or 0.2 or 0.3, something like that. So 1 minus r to the n will still be positive. If you did that with like r equals 2, like we had before, you'd have 1 minus like 2 to the 10th or something, right? Which is going to be negative. So this is just nice because you're using positive numbers instead. Basically, all they did was take the top one and multiply the top and bottom by -1. Right? The top multiplied by -1 distributed into the brackets. We get a positive 1 and a negative r to the n. And on the bottom, we get a positive 1 and a negative r, which is exactly what we have here. Let me get rid of all that notation so you can see it better. But same formula, just happens to be useful if you have an r value that's less than 1, because it'll keep things positive. I don't think we're going to use that in this next problem, though. We have a chessboard, and the way the story goes, the person that invented the game of chess, it was for a king to play, and the king was so pleased with the game that he asked Sissa, who invented the game, what reward he wanted for the great invention. Sissa said he would take this reward. The king should put 1 grain of rice on the first chess square, 2 on the second, 4 on the third, right? So we have 1, 2, 4, and then we're going to have 8, and 16, and 32, etc., right? And it seems like at the beginning, we don't have a lot of grains of rice. And so the king was like, oh, that's not a big deal. It's not going to be a big issue. They mention wheat here, but I've always heard it as rice. So they say wheat. But the question is, how many total grains of wheat will the king have to give to the guy that invented chess? So our U1 is 1. Our R is 2. And how many squares on a chessboard? There are 64, right? So 64, because it's 8 by 8. So then if we put it into our formula, and this is exactly what's given in your formula booklet because both modes are the same, our R is bigger than 1, so we'll probably use the first one. So we're going to do 1 times 2 to the power 64, which is huge, minus 1 over 2 minus 1. And that gives us, I think I have it here. Let's see. It's really big. 1.8 times 10 to the 19. So that means it has about 20 digits. That's a massive number. And underneath they say that the world grows about 1.2 times 10 to the 16 grains of wheat every year. So this is more than the annual wheat production, which is insane. In fact, we could find out how many times more. Let's see. See if I can go to my calculator and divide. So we're going to do 1.8 times 10 to the 19th. 1.8 times 10 to the 19th. And we're going to divide by 1.2 times 10 to the 16th. And we get 1,500. This is 1,500 times more. So you would have to be making rice for 15,000 or 1,500 years to be able to put the amount of, I keep saying rice, but they say wheat, the amount of wheat on the chessboard that this guy requested. So I'm guessing he did not get what he asked for, but hopefully the king gave him some incredible prize. All right, if you want to try these problems on your own, feel free. I'm going to run through them right now. This IB problem down at the bottom, I couldn't find it, but if I do find it, we'll do it when I get back. But I'm just going to run through these three problems here. I've been talking for a long time. You want to try them on your own, try them up at the boards, whatever you want. Let's see what happens. So the students in a school decided to raise money in order to install hammocks in the campus. They have 10 days to raise the required money of 300 euros. The money raised on the first day was 50 euros. Second day, 42.50, and show that there's a 15% increase in the money raised. Okay, so 15% decrease, excuse me. So the way that I see that is we're going to do 42.50 is equal to 50R, right? And we're going to calculate the R value. So I'm going to divide by 50, so we get 50. So 42.5 divided by 50, and we get 0.85. So R is 0.85, which is 1 minus 0.15, so that is indeed a 15% decrease. So we have shown it. Check. All right, letter B. The money raised is 15% less than the previous day. Determine if there will be enough money to purchase the hammock. So what they're saying is this is going to happen for 10 days. So it always goes down by 15%. And the question is, do we reach 300 euros? So our N is 10. Our first term, U1, is 50. And our R value is 0.85. All right, so first day 50, second day 42.50, and it's going to be 85% of each of the previous days. So we're going to have S10 is going to be equal to 50 times 0. I'm going to use the other form because the R is less than 1. So it's going to be 1 minus 0.85 raised to the 10th. Divide by 1 minus 0.85. And let's see what we get. So 0.85 raised to the 10th. 1 minus that answer. Multiply by 50. And divide by 0.15. And I get 267.70. So no, unfortunately, do not get the 300 euros that are required. So now C kind of gives away the answer to part B. How many days do they need? So this time I'm going to do 300 equal to 50 times 1 minus R. We know our R. It's 0.85 to the N. Divide by 1 minus 0.85. So I'll multiply by both sides by 0.15. So 300 times 0.15. And get 45. So 45 equal to 50 times 1 minus 0.85 to the N. Divide by 50. So 45 over 50 should be 0.9. So 0.9 equals 1 minus 0.85 to the N. A little bit of creative algebra. We'll have 0.85 to the N equal to 1 minus 0.9, which is 0.1. And now I'll probably use logs. So let me add a page here. Need some space. So we'll have N is equal to log base 0.85. You could also solve this by graphing of 0.1. Let's see what we get. So I'm going to do log any base. I'm going to math. Here we are. So 0.85 of 0.1. And we get 14.168. So we'll need 15 whole days to be able to have enough to get the hammocks. And part D. After the second day, determine the maximum daily percentage increase in the money they raise if they are to reach their goal of 300 euros in 10 days. Okay, so day 1, they make 50. Day 2, they make 42.50. Whoops. So total so far, They've made 92.50 euros. And so how much do they have left they need to make? So 300 minus 92.50. They still have to get 92.50, 207.5. So what they're asking is if they have an increase in money every day, maybe they can get the 300 by the time they're at the end. So we know that we need 207.5 is equal to our, so our first term now is 42.50 because that's where we're starting from, and we're going to try to increase the percentage each day. So we have 42.5 times, we know our r is going to be bigger than 1 because we're going to be increasing. So I'm going to do r to the power, they have 8 days left, so r to the 8th minus 1 because we've done 2 days already, so we have to increase in the next 8 days. And that's going to be divided by r minus 1. So this, I'm definitely going to solve by graphing because otherwise I'm going to have to do some crazy algebra. So I'm going to go y equals, I wish you could see this, but I'm just going to do y equals 207.5. And then I'm going to do y equals 42.5 multiplied by x to the 8th minus 1 divided by brackets x minus 1. And I'm going to change my window so I can see all the way up to a y max of 215. And the x shouldn't have to go very big because the x value, I mean, what we're solving for here should be like just over 1, right? Because we're increasing by a percentage. So I'm going to make my x go from 0 like to maybe 3. And that should be just fine. So we graph here. I see an intersection point. I calculate, find the intersection, get close to the intersection point and hit enter 3 times. 1, 2, 3. And I get an x value of 0.852. Interesting. What do they say? Determine the maximum daily percentage. Oh, decrease. Yeah. So it's okay for it to still decrease. It just can't decrease by as much. So I get an R value of 0.85211. Oh man, that's heartbreaking. They were so close, right, with their 85%. So the decrease is 1 minus 0.85211, which is 1 minus 0.85211. I get 0.14789. So we were actually quite close, but just a little bit off, which is unfortunate. But if they have just a decrease of just a little bit left, they'll be okay. Okay. All right. So last part, discuss any limitations to this model. So let's see. Trying to think if there's anything that we did in there. Like percentage is only going to make sense between 0 and 100. So percent decrease only makes sense for 0 to 100%. I don't know if there are any other big kind of limitations to this model that would happen. We only have 10 days to do it. It would only make sense to have positive values, so you couldn't do like an arithmetic decrease, but that question comes up a lot in this course just because we want you to be used to seeing it. So limitations here, though, not a big issue. All right, let's try the next couple here. So Roger buys a new laptop for himself at a cost of £495. At the same time, he buys his daughter Chloe a higher specification laptop at a cost of £2,200. Anticipated that Roger's laptop will depreciate at a rate of 10% per year, whereas Chloe's laptop will depreciate at a rate of 15% per year. Estimate the value of Roger's laptop after 5 years. Okay, so he gets it at $495, and it's depreciating at 10%. So we have $495. And this is another one of those sneaky ones where that's like the 0th term, right? That's the first term. So if we're going for 5 years, that's kind of like n equals 6. That means that we depreciate 5 times, right? So we have 0.9 because it's 10%, so there's 90% left. And that's going to be raised to the 5th power. And we get 495, times 0.9 raised to the 5th. Gives me 292.29 pounds. And Roger and Chloe's laptops will have the same value k years after they were purchased. Find the value of k. So we're going to have 495 times 0.9 to the power k is equal to, her laptop was 2200 times 0.85, because it's depreciating at 15% per year, raised to the k as well. So I'm trying to think if there's a clever way you could do this by doing algebra. I don't think so. I think I'm just going to graph both sides. So I'm going to go to y equals. I'm going to graph 495 times 0.9 to the k, or the x. Really handy to get used to solving by graphing in this course, because you can always use your calculator. 2200 times 0.85 raised to the x as well. And I'm going to guess this is not going to take more than like 20 years. So in my window, the value is going to have to be less than $500, because we're already depreciating quickly for his laptop. So I'm going to make my window, my x minimum 0. I'm going to say I'm going to go to 20 years. I don't think I'm going to need that much, but we'll see. The y minimum, I'm just going to go from 0 to 500, because we should see the answer in that window. Oh, nope, it's more than 20 years, because I don't see it yet. So in my window, I'm going to make x go now to maybe 40. And now I see a crossing point. So I'm going to find the intersection. Get close to the intersection point. 1, 2, 3 enters. And I get x equals, or k equals, 26.096 years. So 3 sig figs, 26.1 years. They will be the same value. So validity of the answer. Well, I'm going to say that neither of them are going to keep their laptops for 26 years. So laptops usually die before 26 years. And also, you could say something about the technology, right? Like the technology of laptops is going to change massively after 26 years. No one is going to buy either of their laptops. Also, by the way, the value is, I never know how to make the pound thing. The value is 31.657 pounds after 26.1 years. And I don't think anyone's going to buy their laptops for 31 pounds. Either they're going to give them away, or like, I just feel like this is beyond the time frame that this model would be valid. But anyway, again, they like to ask questions like, well, how valid is this model? What are the limitations? A metal rod 1 meter long is cut into 10 pieces, the lengths of which form a geometric sequence. Ooh, this is fun. So we have a 1 meter long rod, and they cut it into 10 pieces, but they're not equal, right? So the first one might be long, the next one will be a little shorter, the next one will be a little shorter. So they're going to end up with 10 pieces total. I did not do a good job of showing this, but U1, U2, U3, etc., etc. So the lengths form a geometric sequence. So U2 is RU1, right? So they have to be getting shorter. The length of the shortest piece is the longest piece is 8 times length of the shortest piece. So we're going to end up with the last one here is going to be U10. And we know that U1 is 8U10. Right? You think about that either way. 1/8 U1 is U10, or this way, right? So find at the nearest millimeter the length of the shortest piece. Okay. So what do we know? We know the sum, S10, is equal to 1, right? 1 full meter. And I'm going to write that, I guess, probably as 1,000 millimeters, because they want our answer to be in millimeters. So S10 is 1,000 millimeters. And we also know that U1 is 8U10. And how is that going to be useful? Let's see. Well, let's just start putting things into the formula and see what happens. So we're going to have 1,000 is equal to U1, which we don't know at the moment, multiplied by R, which we also don't know at the moment, to the power 10 minus 1, divided by R minus 1. And let's see here. So I think somehow, I know how this is going to work. So U10, we know this in terms of U1, right? So we have U1 is equal to 8 times U1 times R to the power 9, right? That's using our U1 times R to the n minus 1 formula for that. So then if we divide both sides by U1, the U1 disappears. So we have 1 is equal to 8R to the 9th. Divide by 8, we get 1/8 equals R to the 9th. And then we can do the 1/9 power on both sides, or the 9th root. So 1/8 to the power 1/9 is going to give me my R. And R is 0.7937. Whoops. r equals 0.7937 with some extra decimal places on there that I'll hang on to, but I'm just writing down to 4 sig figs for now. So now we know 1,000 is equal to U1, which is the only thing I don't know now, times 0.79, whoops, 7937 raised to the 10th minus 1 divided by 0.7937 minus 1. I suppose I could have used the other form, the 1 minus, but it doesn't matter, right? We're just going to deal with negative numbers here, which is just fine. So the 0.7937 minus 1 is negative 0.206. I'm going to multiply that by 1,000. So we have negative 206, whoops, 0.299 is equal to U1 times, I'm going to do that 0.7937 to the 10th power, which is 0.09921 minus 1. Add a page here. Whoops, this one. A bit more space. We're almost done, which is good. Got an extra parentheses down there. And now all we have to do is divide. So that 0.099 minus 1 is negative 0.99. So we have negative 206.299 equal to U1 times negative 0.9007, about negative 0.09. So U1, if I divide the negative 206 by the negative 0.9, we get 229.02. So what does that mean? That means this first one is 229 millimeters, or I guess about almost 23 centimeters. And so then we know that the shortest piece, because that's what they ask for, is 1/8 that size. So U10 is 1/8 times 229.02. Whoops, that was a very curly Q2. And that is equal to, we divide by 8, 28.627. All right, millimeters. And they asked to the nearest millimeter, so about 29 millimeters. So, lots of stuff about geometric sequences and series. Please do try the problems on the outline. I believe they're from chapter 7. And I love you guys. That's why I'm here. Hope you have an excellent day, and I will see you soon.